welcome everyone. I'm glad you could take some time out of your busy schedule to attend our webinar today, and hopefully you will find it useful for troubleshooting and your everyday activities in the laboratory. Today's presentation, practical steps in GC troubleshooting, we're going to cover a lot of details. We're going to cover different ways to identify problems with chromatography. We're going to look at different examples of what the poor chromatography might look like, and we're actually going to go into some really good troubleshooting, so how you can actually go in and work through those problems using some techniques that I'll share with you. So when we're looking at these problems in chromatography, we try to figure out, what went wrong and how to fix it. So you're going to be confronted with common problems that you'll run into. Again, and we'll look at some troubleshooting tools, and we'll actually show some examples on, once you've done the troubleshooting, using the troubleshooting tools, what the example would look like, and if your troubleshooting has paid off. So when we get into this, it was like everything was just fine, and then something happened. And this is very interesting. So what I will do is I will go away from some of the slides and share with you some personal experiences. I talk to customers every day on the phone, and every call presents a different challenge. So again, these are very timely type of phone calls we get. These are things that we monitor, things that we keep record of to try to help our customers with the same problems that come up from time to time. So again, we look, that everything was working well, and something happened, and how do I go about troubleshooting? So you really got to think about this, and while I make this sound very simple, I realize that your goal is to run samples, to get the results you needed for your analysis, to move product, et cetera, So, but unfortunately, when you do call tech support, there's a series of questions that we have to go through to really help and get, to the bottom of the issue. And again, I understand your frustration. I understand that, they're asking me these redundant questions that, that I know I've done or I haven't done or whatever. But I can assure you the intent is to help you in any way that we can. Again, some of the questions will be redundant. We go through some things, but they're some of the smallest details that can create some of the biggest problems. So when we're looking at these things too is, we look at it and say, well, everything was just fine and this happened. So what we want to do is we want to use logic. Something changed. Was it slowly or suddenly? But we do know that something is different. The thing I would recommend to you, in any case, I don't care how you do this with a Word document, I don't care if you track it in the user software for the instruments, whatever, but just remember to track the events. A logbook or some type of diary will really help you troubleshoot. And the things that would be included are that you change the column, the liner, the septum, the syringe, etc. Now, what a lot of customers think is, I just changed, I just put a new liner in, or I just put a new column in. How could there possibly be a problem with a new product? Well, there can be if the product wasn't handled properly, or if the product wasn't manufactured properly. The other thing we'll look at is injected samples. Is there a particular sample that every time you run this sample that you have other problems with your other methods? That stuff needs to be, documented so you know for sure after you run that difficult sample or problematic sample that possibly you go in and do maintenance after that. And have you been doing maintenance? Did you cut the column, the inlet, and things like that? So what we're going to do is we're going to break this down to start off with the logical troubleshooting, and we're going to look at, there are 5 basic areas from where the problem arises. the injector, the flow, the column, the detector, or possibly the electronics. But remember, it can always be some sort of combination of both of those things. You know, the inlet could be creating some of the problem, followed by the column and the detector. And knowing what you can't and can't cause the system is key. What I will share with you is with our statistics that we keep, that many of the problems that customers struggle with is the improper setup of the injection port. Now, in this troubleshooting seminar today, we will not go into the individual mechanics of the inlet. There are other e-seminars that I would request or like you to attend where we really go in and we specifically focus on the inlet. There we go into great detail. You know, for a 1-hour e-seminar, it's very difficult to try to cover each one of those components in great detail. So please review the e-seminar program and look for things that you feel might help you. We do them on inlets, columns, detectors, care and use of columns and inlets and things. So you might want to consider that in the future. But for today's logical troubleshooting seminar, we're going to look at the five issues here. Again, the injector, the flow, the column, the detector, and electronics. And how do we troubleshoot these overall? So over the next few slides, actually the next number of slides, what I'm going to do is talk about typical problems of optimized methods becoming unoptimized. You know, what happened and the reason why. And we're going to cover all of these topics, starting with peak tailing, bonus peaks, split peaks, no peaks, all the way through shifting retention, baseline disturbances, and finally, quantitation problems. So, as I mentioned, we're going to go through these one by one. So let's first look at peak tailing. If we're looking at peak tailing, it's usually caused by the injector or the column is active. There could be, or it could be caused by the reversible absorption of active compounds, you know, with the OH groups, NH groups, or SH groups, and they can, again, cause reversible absorption for these things and create this type of peak tailing. The other thing that can cause it is a flow problem. If there's dead volume, if there's a partial instruction, and probably the number one issue is poor installation of the column, followed by severe column contamination. I want to tell you, again, talking to many customers, and I know some customers possibly cringe when I mention this to them, is that column installation is probably one of the most difficult and problem to troubleshoot, because once you install a column, you know, if you did take the time to cool down the inlet and all those things, when you're dealing with these very small column nuts and ferrules and things, and once you know, got a new column in, or if you cut the column and reinstalled it, a lot of customers are very reluctant to say, you know, I'm not going to go back in and check that column again. But I can tell you, if that column slides down too far, or if that column is extended too far into the inlet or detector, these type of tailing peaks are very common. So please, when you're going to install a column, and again, as I mentioned, we covered this in quite detail in installation and column selection e-seminars, it's really important that you really take the time to do it right. So if you do have a problem, that when you call tech support and we ask you to check the installation, that you don't, you know, say, oh geez, I don't want to go through that again. You know, those small parts, they're hot. But please, when you change a column, if you trim the column, please take your time and do it right, so we don't have to go back and check it again. The tip here is to inject a light hydrocarbon, and it should not tail unless there's a flow type or a flow path problem. The tailing peak can also be common with overloading of a plot column, a porous layer, open tubular column. Can be coelution, polarity mismatch between the phase, solute, or the solvent. And some compounds like these amines, they can tail. They tail a lot anyway. So please take your time when you're installing those columns. But again, most of the time we see this stuff is either poor column installation or flow. So the next chromatogram, let's look at bonus peaks. So if you're looking at this chromatogram here, we have a number of peaks on this chromatogram, and you can see there's the width of the peaks we're looking at, and you can see that we have a 0.29, a 0.30, but all of a sudden we have this peak, this tall peak. It's not Gaussian shaped. It's just not a good looking peak. A lot of times that is going to be from a contamination or something. So again, when you see a peak like that that doesn't belong, a lot of times it can do with contamination. Now let's look at bonus peaks or ghost peaks. Ideally, what we're going to look for is we want a nice flat baseline. If you look to the left of the slide, the bonus peaks can be the effect of contamination in the injector, column, or flow from the carrier gas. It also can be carryover from backflash or previous sample. Also, don't ever rule out a bad tank of gas or traps that are totally expired or contaminated or used up. These bonus peaks can also be called from septum bleed. While rare these days, they could be septum bleed. But again, my tip to you is when you're troubleshooting is always to run a blank run. Ideally, when I talk about a blank run, I tell the customer to actually remove the auto-sampler syringe from the auto-sampler. What this does, this truly gives you a baseline from the septa to the detector. Again, by removing the syringe and injecting nothing, you have eliminated the possible problems you have with the auto-sampler, possibly the solvents being contaminated, the vials being contaminated. So again, a true blank run, what I would recommend to you is to remove the syringe from the auto-sampler and do a blank run. And again, it should be, when you do that, it should be nice and flat. Okay, so let's look at the next topic, which is split peaks. Ideally, again, on the left of the slide, we want this nice Gaussian-shaped peak. And what happens when we get these split peaks, these smaller split peaks? We get this shoulder peak and a peak before the solvent or peak. So in most cases, this can be caused by poor sample introduction. It can be caused by injecting the sample twice. And how do you do that? Well, if you're not careful, if your plunger is jamming in your auto-sampler or your manual injection, you're actually doing a double injection and you can get a split peak. The other thing you have to be careful with too is when you're making up your samples, ideally you don't want to use a mixed solvent. Again, primarily, if at all possible, you want to use one solvent because those solvents, when they are volatilized in the inlet, are going to flash at different temperatures, and you can get this type of peak shape. The other thing that can happen, it could be the sample in the syringe needle. So it may be a good idea is to change your injection technique, have someone else do a different injection, or again, do a manual injection. This peak shape can also be caused by injector activity. This could be breakdown. It's really not a peak. It's actually two peaks. It could be sample degradation in the injector. The important thing about the sample in the injector is that we want to make sure that we have the inlet at a high enough temperature to make sure that all of the compounds are boiled or vaporized, volatilized, and that we and that we don't make it too hot. For instance, if we were looking at pesticides, if we had the inlet too hot, we can actually cause degradation of those compounds. So the inlet parameters are very important. The other thing that we can look at with volatility is, again, the high boilers could be dropping out on cold spots. So we want to make sure that the sample path is warm throughout the entire, from the inlet right to the detector. I've run into this before where the transfer line heater may fail, and the customers are looking at these split peaks and say, what's going on? And the transfer line temperature that is not optimized or is not high enough. The other thing with these type of peaks can be caused by unions or fittings not tracking the column temperature. That's why when you look in our instruments that the fittings, you're saying, why do they use such small fittings? Why is everything so small? Well, the problem is we want minimal dead volume, and we also want minimal heat sinks. You know, it'd be nice to have a big, you know, column nut that you could put on there, but the problem is the more mass you have in metal, when it's heated, you create these huge hot spots. So there are reasons for the things that we do with the smaller fittings. Okay, so let's look at another example of no peaks. The simplest way to look at this is, well, maybe the detector is not working or is not operational. The other thing is, just give me, the other thing could be the injector's not working. The third problem could be that it's a plug syringe. It's not moving. I've actually had customers go in and actually select the wrong injector or the detector in the chem station and actually be monitoring the incorrect detector. It could be a huge leak, and believe it or not, it could be no carrier gas flow. I can tell you I've had customers run out of carrier gas and say, I'm not getting any peaks. So please look at the basics. Go back and make sure we have those basics covered before we start tearing the system completely apart. The other thing it could be is a broken column or no column. But believe it or not, some customers will call and they see these, you know, when they see extra peaks. You know, a lot of times customers will talk about, well, I don't see any peaks or I see extra peaks. And I can tell you that a GC column will not create distinct peaks. It will create an elevated baseline at a high temperature, but the column itself cannot create peaks unless something is actually coming through the system, that the column is actually separating and you're actually seeing a peak. Okay, so the next one we'll look at is peak response. That if you look at the, again, the desired chromatogram on the left, what's causing this? It can be a leaky syringe. Please remember, syringes do not last forever, but the care and maintenance of that syringe is important. You know, if you're dealing with some really dirty samples or problematic samples, please go in from time to time and manually clean that syringe. Here, this could also be caused by the split ratio being set incorrectly. So if you don't have a flow meter, you need to have one to be able to double check to see if the instrument is operating properly. This could be caused by the wrong purge activation time. So again, check the method and make sure everything is correct. This could be caused by a septic purge that's too high. On a lot of newer instruments, you can't adjust the septic purge. But somehow, if the septic purge gets out of whack, or it becomes at a very high or very low purge, with a very low purge, you will start to see more contaminants and a higher response. At a very high septic purge, you could actually have samples sweeping out of the inlet, so your response would be decreased. Also, please check and make sure the injector temperature is correct. Too low will, again, affect the volatility in the response to these compounds. What might cause this on a detector? The settings or flows have changed, and the electronics could be failing. So again, it's important to look at everything in this case to make sure you've covered your bases. And again, I can't emphasize how important it is to have some type of flow measuring device, even if it's a manual bubble flow meter, to go ahead and double check the flows at different times. Okay, so this is always a particular one that could be a little more tough to diagnose or troubleshoot. So again, on the left is our desired chromatogram, and what we're seeing with the next chromatogram, we're seeing the peak in the middle that has really, the response has really fallen off. And again, that could be the effect of an inlet or column that is active or contaminated. Again, it can be caused by the irreversible absorption of active compounds with these OH, NH, and SH groups. It could be the decomposition of your sample. A temperature change can cause this, as well as evaporation of the sample. And again, the tip here, if only some change, then ask which ones. If it's the active compounds, and then it's probably activity. If it tracks the volatility, then the cold spots, it could be cold spots or inlet discrimination. So look at the compounds. The other thing I would add here as well is that, you know, some of the later eluting compounds, if they start to have problems with peak height, a lot of that could be due to either the flows not being properly set or just the transfer line on the mass spec in some cases not being hot enough. So again, try to check everything. The other thing, let me mention here again about the evaporation of the sample. You know, a lot of people, when they look at activity and they look at peak response, you know, a lot of people don't even think about the vials, you know, but please remember, if you do have samples that are reacting with, you know, UV light, or if they're light sensitive, please make sure you use the proper vial, you know, like an amber vial. And also, please check the integrity of your vial caps. Make sure that you're sealing those vial caps properly, that you're doing either a good, you know, crimp. Also, if you're using a screw top vial, make sure you tighten that screw top vial, but do not tighten that vial enough that you get a vacuum on it. So you can actually do this in the lab. Take a screw top vial and tighten it as tight as you can, and actually you will actually suck in or indent the septa. So it's important to double check those things if you start to have a problem with peak response. And the next topic we'll look at is peak fronting. It's either called a shark fin shaped or just slight. And sometimes this is due to column contamination. In a lot of cases, it's due to column overload. You're just injecting too much sample on the column, and the column does not have the capacity. Now, you know, probably 70% of our customers use the split mode, and so they are sending off quite a lot of sample prior to going to the column. But if you do see this fronting, make sure that you're not overloading the column, that the sample is not too concentrated. There's an easy way to look at it: either inject less, increase the split, or just double check your dilution and make sure you haven't actually not done enough dilution. In the injector, this can also, again, be caused by column installation. I talk a lot about column installation, but you got to be real careful, because if you don't install it right, you can get all kinds of different peak shapes with a poor column installation. Also, it could be caused by the compound being very soluble in the injection solvent. There you might need a retention gap. We could have this mixed solvent again, or it could be coelution or breakdown. And let's look at the next one, which is retention time shift. Again, the chromatogram we'd like is on the left. The one on the right is what we're experiencing. A lot of times this can be a leak in the septa. It could be a change in the injection solvent. It could be a large change in the sample concentration. This can also be affected by the flow. So check or double check the change in gas velocity. And these retention time shifts can be caused by a grossly contaminated column, a damaged stationary phase, loss of a stationary phase, which would decrease retention, and a change in the temperature. And here is a gross example of an overloaded column. So at the top, you'll see there's an injection of 1,400 nanograms, and you can actually see that it decreased the retention, and the peaks are looking really poorly. And at the bottom, you can see a better separation between the peaks at a 7 nanogram per component injection. So please don't overload the columns. Now, if we look at a loss of resolution, again, here we have separation, we have peak width, and resolution is a function of separation and peak width. And a loss of resolution actually ends up being a separation decrease. And what causes this? The column could be at a different temperature, contamination, more phase. It could be matrix components co-eluting, and it could be just a different column phase. Okay, so you want to be careful with this. Also, a loss of resolution equaling peak broadening. A lot of times this is charged by flow, so a change in the carrier gas velocity. Makeup gas not properly set can be a problem. It can be caused by column contamination, phase degradation, and injector efficiency. So double check the method. If it worked before, go back and make sure that we have the right settings, that the liner's the same, that the column installation is good, etc. In baseline disturbances, sudden changes, wandering, or drifting. So if you look at the top here, this is wander. And a lot of customers will say, no, this is column bleed. This is not column bleed. This is something that's coming through the system that's causing the baseline to wander. It can be caused by the column or detector. It could be caused by not fully conditioned or stabilized electronics. So if you were to put a new detector cell in, or if you were to do a lot of maintenance on your FID and the instrument hasn't settled down, you can get this kind of wandering baseline. The other thing that can cause it is flow, changes in the carrier gas or detector flows, and it can also be caused by valve switching or leaks. Okay, so if we look here again, we look at a noisy baseline, the top mild one here is not bad. You know, that's, you know, we'd like it cleaner than that. But the one at the bottom or the middle of the page is severe. And again, this could be caused by contaminated gas, incorrect detector settings. This may be bleed if at a high temperature, but remember, column bleed only happens at the upper temperature of a GC column. It will not be caused at a lower temperature or, you know, well below the upper temperature of the column, so don't confuse it. Most customers, and I love you all, forgive me, but many people, you know, focus on the column as being the problem, and in many cases it's not the column, it's other things associated with it. It could be another issue within the detector flame, poor installation. So in this example, in detector flame, poor installation, when we tell you to install the column, and again, we do cover this more in the installation of GC columns and troubleshooting, is when we ask you to install a column in an FID, we ask you to put it through the column nut, through the ferrule, and cut it, because we want to make sure we don't get any column material or ferrule material in the column. And then we ask you to feed that up slowly to the top of the detector after, you know, you want to make sure you got a good cut. And we ask you to feed it up slowly till it stops and back it down a millimeter. The reason we do that is because backing it down the millimeter, once you're starting to tighten the column and the ferrule grabs the column, it's going to push that column up into the FID. If you don't leave that 1 millimeter space, what you'll do is when the column ferrule grabs the column, it will jam it up into the FID jet and it will partially plug it or corrupt it, and you'll start to get these really, severe or just noisy baseline. So please be careful. Okay, from a detector side here, this could be an air leak, and it could be also an electronics malfunction. So the next topic we'll look at is spiking baseline. A spiking baseline could be from particles entering the detector if you're using like a plot column. It could be a poor connection, or again, this could be caused by cycling of equipment, electronics in other places of the lab. That's why when we ask you, when you install a new GC, that you have it on a dedicated line. That dedicated electrical line for that instrument will eliminate these type of spiking from other equipment on the line. Okay, now let's look at some quantitation problems. From the detector side, it's poor stability, electronics, or baseline disturbances, contamination. The other thing that could be outside the detector's linear range. I mean, you could have the detector, many times customers will call in and they'll say, wow, I'm seeing all this baseline, but what happens is they have zoned in or have focused so low on the noise that the chromatogram actually looks like it's really noisy, but if you went back to your default settings, you wouldn't see those erratic baselines. So be careful about how you scale the chromatogram as well, and especially if you've had problems, make sure your scaling is correct. Make sure you're comparing, I want to say, apples to apples. Okay, that's very important. The other thing from quantitation, it can be from activity in the absorption in the injector or the column. In the injector, it could be the technique, the settings, the condition. It could be caused by a worn syringe. Again, the syringes do not last forever. The other thing, think about it, it could be coelution, matrix effects, sample evaporation, leaky vials. I talked about that a little earlier. And actually sample decomposition. The sample integrity is critical to this. A lot of customers start and they go right to the GC or the column and start troubleshooting without going back and taking a real good look at the sample handling or the integrity of how the sample was made up. So moving into the troubleshooting tools, what we're going to do is we're going to look at the bleed profile and baseline problems. We're going to talk about, or I'm going to talk about injecting a non-retained peak and peak shape problems. We'll look at the test mix. We'll isolate the components, all problems. We'll do some condensation tests to look at baseline problems, and jumper test tube to look at baseline problems. Again, this presentation you will have. This presentation is recorded. You have the PDF of it. I would request, if at all possible, keep it for future troubleshooting. So I want to spend a little time on this slide, and let's talk about generating a bleed profile. What I would recommend that everyone does is when you get a brand new column, once you've conditioned the column properly, again, after following meticulous column installation, the proper cutting the column, not over tightening the ferrules, conditioning the column properly. Again, we get this call. Most GC columns, and I can tell you all Agilent GC columns are pre-conditioned prior to you getting them. So the requirements of newer GC columns, the conditioning time is much lower. So if you look at this chromatogram here, what we've done, we've taken a DB1, a 30-meter column, and after we've conditioned the column, we've run a bleed profile. And this, if you follow my pointer, is what you would expect from bleed on a new column. You're going to get some rise in temperature. Again, this is at 320, near the maximum temperature. What I would recommend to you is when you get a new column, that once you've installed it and make sure you don't have any leaks, and you condition it, that you do a bleed profile so you have it for future reference. Okay. The other thing is how do we look, or why would we use a non-retained peak? It's used to check the flow path. In a GC column installation, a good installation will create this Gaussian type peak. It's going to look really good. If the column is installed improperly, or you have an injector leak, you'll get this type of peak. So please, I can't emphasize enough to you that when you do install a column, please take the time and do it right. It's really going to be important. The other potential problems that can be from this type of peak is the injector or septum leak. I recommend, you do inlet maintenance according to your schedule. This could also be caused by the split ratio being too low. This can be caused by a liner problem. It could be broken, leaking, or the wrong liner. And again, the column positioning. So this is the chromatogram you get with a brand new column. This is the chromatogram for what you would get in the box, and you can actually see we go through great pains to make sure every column is tested. And also on many of the columns, we actually have the bleed specification mentioned on the column. And in our test mix, if we look back here, it's critical. We use a very probative test mix. And what we do is we use hydrocarbons to measure column efficiency and retention. We use alcohols to look for activity. We use FAMEs or PAHs to measure retention. We use acids to measure the acid character and bases to measure the basic character. So again, we use every compound in our test mix to make sure that every column you get, again, is going to meet our stringent specifications. And again, every column we sell is pre-tested, pre-conditioned, and every column has the bleed run on it. The other thing I would recommend to you too, when you get a new column, I'd recommend you use your own test mix. It's going to be more specific. You might be using a selective detector that we don't use. Most GC columns are checked out on a flame ionization detector. The other thing you're going to see about this, using your own mix, is going to be your actual concentrations, and there's no conditions or instrument changes. So you're familiar with this test mix. It's always a good idea to run that on a new column. And what you want to do is when you're trying to figure out and start troubleshooting, you want to isolate the components. If you are having a problem and you think it's a column problem, put in a known good column. Or if you think it's the column, move the column to a different GC, an inlet or detector. And also, if at all possible, simplify the system. Example, if you're using headspace or purge and trap, try a direct injection. Split the system up. That will tell you if you're having a headspace problem or purge and trap, or if it's a GC. Okay, now I'm going to talk a few things about some tests we do. This is the condensation test. This is used to isolate the cause of erratic baselines or ghost peaks or carryover. Use this when problems are worst after the periods of GC non-use. So the procedure is for the condensation test is to leave the GC at 40 to 50 degrees overnight, do a blank run, repeat the blank run immediately after the first blank run is complete, and compare the two runs. The results, if the first blank run is worse, the contamination is from the injector, the lines, the traps, or the carrier gas. It's being carried into the column. If the blank run's the same, the contamination is strongly focused on the front end of the column, so you'd have to go in and cut the column or remove some of it where the contamination is. So let's look at the jumper tube test. The purpose is to help locate the source of the contamination or noise, and it isolates GC components. So in the jumper test tube, let's isolate the detector. We're going to remove the column from the detector, we're going to cap the detector, we're going to turn it on, and we're going to do a blank run. If the detector is flat, it's okay. We've isolated that. We know that if we get a nice flat run, that the detector's okay. If the detector gets this wavy baseline or noise, we know it's a detector problem. So again, refer back to these slides as needed. So let's do a jumper test to isolate the injector. We connect the injector and the detector with 1 to 2 meters of fused silica tubing. We turn on the carrier gas, we run a blank run, and If we get a blank run, the injector's okay. Again, so we know the detector's okay, and now we've hooked a piece of tubing from the inlet to the detector. If we get a nice flat baseline, we know the injector's okay. If not, this type of wavering here can be the injector lines or carrier gas is contaminated. Okay? Moving forward. So let's do a jumper test tube to isolate the column. We reinstall the column, we set up as before, we do a blank run, and if the problem returns, right, because again, with our previous tests, we made sure the inlet was okay, and the detector was okay. In our previous tests, we made sure the inlet was okay. So now when we put the column back in, if the problem returns, it's got to be the column. If the problem's gone, it must have been previously a leak or solid debris or installation problem. Okay, so now let's do some troubleshooting. And again, please take the time, if you're going through this, to look at the chromatograms that I showed you before, and the jumper test tube is very helpful for troubleshooting when you have a problem like this. So again, let's do some troubleshooting. Well, example one is customer calls, says, I get no peaks. So the sequence we go through is, okay, so first of all, let's do logical steps taken to find the peaks. Most of our problems are leaks and plugs. So the first question we're going to ask, and again, it's meant to no offense to anyone, is the FID lit? Put a piece of glass over the FID outlet. If the water condenses, it's lit. Or if you monitor the signal, if you see the signal above 2 or 3 picoamps, the detector is probably lit with the FID. Also, look at the output, again, as I mentioned in the instrument, and make sure that the signal is higher than 0, and you could probably make sure, you'd be sure that the detector is lit. So the newer, very clean FIDs will exhibit maybe 2 or 3 picoamps. If the detector is a little dirty, it might be as high as 16. Okay, so the detector's okay. Next thing we'll look and make sure there's flow through the column. We'll disconnect the column from the detector, and we'll measure the flow with a bubble solution per meter. So if we just disconnect it from the detector, already we made sure we have a flame. If we have flow, we'll move on. And then we'll assess the observation. If the flame is lit and we have flow through the column, the sample is not getting on the column. You know, is it the syringe plugged? So the ideal thing is take the syringe out of the GC, pull up some sample, some solvent, and manually dispense it onto a chem wipe. If the towel stays dry, the syringe is plugged. So again, pull the plunger out, add solvent, replace the plunger, and this will dislodge. It could be a septic particle or something else. So again, make sure that the syringe is actually expelling the solvent. And finally, we have peaks. So again, we're looking for flow. We're making sure the detector's lit. We're making sure the column's not broken. And we're making sure that we're injecting the sample. So let's look at another example. This is a DB624 column. Here are the components within the mix here we're looking at. And this is actually the test mix for the column. So look at the next chromatogram. We're looking at column contamination here. This is a same column after 75 injections of an oily sample. So what's happening is this column is becoming a different thing. This oily material is probably contaminated the liner and has started to head toward the column and starting to actually coat the column. So if you look at this slide, please, this is a liner, a gross contamination of a liner. This is all types of non-volatile or partially volatile material that's in the liner. And you can actually see here is a good column, a good part of the column, but this is actually a coil, the first meter of a column that's completely contaminated. So again, you don't want to get to this part. This has to be maintained and addressed prior to this kind of contamination, because the more it's contaminated, the harder it's going to be to get it out of the system. So what we did is we remove on this same column, remember it looked like this, so we started our troubleshooting, we cleaned the liner, and we removed the first 1.5 meters of the column from the injector end. And when you can actually see, the chromatography has improved quite a lot. But this can be deceiving, okay? So when you have a column, typically we ask you to remove one wrap. One wrap of a standard 7-inch basket is about 1/2 meter. So again, when you're removing column, customers ask me all the time, well, how often should I do that? If you have clean samples, or if you're not doing any injections, you don't have to do it ever. But if your samples are fairly dirty and you start to see your responses change, more tailing, it's probably indicative that the inlet and the column's being contaminated. So you're going to have to get to a point where after so many injections, specifically if your samples are dirty, that you have to do maintenance. And that could be liner and column cutting or whatever it requires. So here the column looks much better. But again, it looks fixed, but look what happens. This is the same column that we've already cut. And look at the contamination that's still on the column. So that material has migrated down that column more than 1.5 meters. And even though it looked better, it's still contaminated. So what you can do, and this is very rare, customers can rinse columns. It's important, though, that you understand how to rinse them, and you always rinse the column from the detector back. You don't want to rinse it from the inlet, because you're going to push all that contamination from the inlet in the front of that column through the rest of the detector. There was old philosophy, there were old practices, where customers thought that they were cleaning their column. They would do large volume injections of solvents. And the problem is when you do a large volume injection of solvent, when you think you're doing column cleaning, you're actually taking all of that material that's in that liner and in the front of that column, and you're rinsing it through the rest of the column. So please don't do that. The other thing I'd like to add, I've done this for quite a while, and the thing I'd like to add is, I'm not going to tell you to do things that if they do work for you, don't do them. I meant the philosophy, if it's not broken, don't fix it. But please, just think about what I said. And if you're doing these large volume injections of solvent, and remember, you're washing all those contaminants through the column. So it's better to trim the column or rinse the column by backflush. So again, if we go back and highlight the jumper tubes test, we use the jumper tube test. It's used to isolate the source of contamination. Again, cap off the detector and establish normal gas flows and temperature. Plot the baseline. If it's flat, the detector's good. Connect 1 meter of deactivated tubing between the injector and detector. Plot the baseline using a temperature program. If it's flat, the inlet's fine. Install a column and plot the baseline using the temperature program. And this is a contaminated inlet. This is what a contaminated inlet might look like using the jumper test tube. Now, I'm going to show you this slide here. I want you to be very careful with this, because you can certainly rinse the injector, but you must be careful if you have a very highly contaminated inlet that you unhook the EPC. And using the procedure here, you can actually rinse the inlet weldment. I would recommend that you remove, in a split slitless inlet, the gold seal and the reducing nut. You place a beaker in the inlet, and you use a series of solvents to clean the injector. However, do not use any abrasive brush on this inlet. I don't care if you use a Q-tip, something soft, but what you don't want to do is go in there with a really abrasive type brush and change the integrity of that inlet. So again, you can clean the inlet, Q-tip and solvents, just be very careful. And finally, looking at troubleshooting tips, let's isolate the problem. A blank run is your friend. Injecting an unretained compound is your friend. Using the jumper test tube is very helpful, the jumper test. When you're troubleshooting, change only one variable at a time. I can't tell you how many times I've talked to a customer where they've changed the tank of gas. And they changed the tank of gas a week ago, and within that week, they've ripped the injection port apart, the column, the detector. They've done weeks of troubleshooting, and it all comes back to not remembering the last thing they did. They changed the tank of gas, and the gas was contaminated. So please change one variable at a time. Always remember to compare before and after chromatograms. Like I said, when you get a new column, if you want to run after you've conditioned it, you know, they do come pre-conditioned, but after you do your conditioning, if you want to run your sample on it, fine. It's a good idea to have that chromatogram, or run your bleed test on it and put that with the original box. I would always keep the original box as well. That original chromatogram that comes with our columns is the original chromatogram. It's not printed off on the plotter. Back to comparing before and after chromatograms, please look at the peak shape, the response, the retention, the baseline rise, the background, and look for trends. And as always, you can always call our tech support department. In the United States, our group is available from 8 to 5 all time zones, and we're here to help you. Again, but in many cases, we're going to ask you a series of questions, and unfortunately, it's really the only way to get to the bottom. We really want to help, but we need to, have a few questions up front to make sure to know what you've done and not done as far as troubleshooting. And again, remember, it's a complete system, right? Carrier gas, the injector, the column, the detector, the data system. It can be a multiple cause and effect, and does not change too many, and again, do not change too many variables at once.